I just got Tesla's full self-driving 12.3 and it is remarkable, amazing, incredible, but it still has something of an Achilles heel, and that is the midterm planning, the 20 to 30 second planning regime. And while I found that somewhat disappointing, Yann Lecun with Meta might actually have a solution, and it's really interesting. Let's take a look. Hey y'all, it's Dr. Know-It-All. I am going to use a recent Lex Fridman Yann Lecun interview, just a couple of minutes from it, as a means of discussing Tesla's full self-driving 12.3 and what I still perceive as a significant architectural problem with it, and how what's called V-JEPA, or Visual Joint Embedded Predictive Architecture, might end up being a solution. Of course, this is just a couple of minutes from a 2-hour and 45-minute incredible interview. It's really, really amazing. I will leave a link in the description, of course, so you can look at it. Highly recommend you watch the entire thing, probably more than once, which I have. So Visual JEPA has to do with hierarchical planning, and I want to let Yann talk about this in his interview. This starts around the 45-minute mark. I'll actually leave the little play button up. In fact, you can see it right here. I guess it's 44:21. But anyway, this will let you go straight into that specific spot and actually listen to that particular moment. But I want to let him talk about it, and I'll kind of skip around a little bit, but then I'm going to go to the article that was published by Meta actually a month ago now. I can't even believe that. I have actually been sitting on this for quite a while. I was number one, a little bit scared to talk about it because I was like, I want to really kind of understand this at a fundamental level before I talk about it. But I also kind of wanted full self-driving 12.3. And as it turned out, both of those things happened relatively on top of each other. So I feel comfortable talking about this now, although, you know, I'm certainly no expert in joint embedded predictive architecture, but I think I can talk about it. So here we go.
You also often talk about hierarchical planning.
Yeah.
Can hierarchical planning emerge from this somehow?
Well, so no, you will have to build a specific architecture to allow for hierarchical planning. So hierarchical planning is absolutely necessary if you want to plan complex actions. If I want to go from, let's say, from New York to Paris, it's the example I use all the time, and I'm sitting in my office at NYU, my objective that I need to minimize is my distance to Paris. At a high level, a very abstract representation of my my location, I will have to decompose this into two sub-goals. First one is go to the airport. Second one is catch a plane to Paris. Okay, so my sub-goal is now going to the airport. My objective function is my distance to the airport. How do I go to the airport? Well, I have to go in the street and hail a taxi, which you can do in New York. Okay, now I have another sub-goal. Go down on the street. Well, that means going to the elevator, going down the elevator, walk out the street. How do I go to the elevator? I have to stand up from my chair, open the door of my office, go to the elevator, push the button. How do I get up from my chair? Like, you know, you can imagine going down, all the way down to basically what amounts to millisecond by millisecond muscle control. Okay. And obviously, you're not going to plan your entire trip from New York to Paris in terms of millisecond by millisecond muscle control. First, that would be incredibly expensive, but it will also be completely impossible because you don't know all the conditions of what's going to happen. You know, how long it's going to take to catch a taxi or to go to the airport with traffic. You know, I mean, you would have to know exactly the condition of everything to be able to do this planning. And you don't have the information. So you have to do this hierarchical planning so that you can start acting and then sort of replanning as you go. And nobody really knows how to do this in AI. Nobody knows how to train a system to learn the appropriate multiple levels of representation so that hierarchical planning works.
Okay, so let's stop there. There's a lot to unpack in this. The first thing is, and he does a good job, this is a good explainer. It's like, you know, you want to do something that involves multiple steps. You don't plan everything out. Like if I wanted to go to Paris right now, I would have to go online. I'd have to look up, you know, plane flights. I'd have to buy a flight. Then I would have to go get to my car. Then I would have to drive to the Atlanta airport through traffic that is unknown, right? That's part of what he's talking about is you don't know the future. Get to the airport in time, go through security, blah, 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 get on the airplane, get to Paris. catch a cab or an Uber or something like that there, get to my destination at the hotel. All of these things have to happen, and they have to be planned out in a top-down manner. We just got back from Whistler in British Columbia, and there are many steps to planning that trip, right? And many of them you don't know until you actually get there. Like, for example, the hierarchical planning of purchasing the lodging and purchasing the tickets was one thing, but then we had to get the transportation. We had to make decisions about whether we take a car or whether we take a shuttle bus. And then when all of that happens and the flights get delayed and suddenly plans change and you have to, suddenly hire a private shuttle service instead of the public bus that you were going to take. So everything got really expensive all of a sudden. So all of those things happen. And then, when we get there, we don't know exactly where our hotel is, and it's a large village. And so we're on foot and we're having to discover where this place is. All of these things cannot be planned out in advance in detail. And in a smaller, ecosystem here. So you've got, let's just take a car ride. So let's say that I'm going to go in 12.3. I'm going to use FSD 12.3 and I'm going to go to the airport. So that's approximately 75 or 80 miles from our house. And so the car is going to get the Google Maps, hierarchical top level planning, but then it has to stream down from that, like he's saying, millisecond to millisecond. The first thing I would have to do in order to drive to the airport is get up from this chair. I'm in a chair. How do I do that? There's a lot of muscle control and biological activity that has to happen just for that first step. You can't plan everything at that level of detail. So Tesla has got, full self-driving, has got the top down view. It's got the Google Maps. So it knows where to go. It knows the roads to get on. It knows what lanes to be in. It knows which exit to take, all of that kind of stuff. And it knows the kind of second to second planning because that's looking around it and going like, oh, there's cars right there. I can't drive at 65 miles an hour or else I'm going to rear end that car in front of me. Or that guy just cut me off, and so I need to slow down and move out of the way or something along those lines, right? So it's got the top level, and it's got kind of the microsecond by microsecond level of things taken care of. The problem, and this is what I always talk about, is that middle section, that 20 to 30 second planning section, where it's like, okay, this is what needs to happen next, right? I'm driving and I know that what I need to do is be able to get off the exit right now, or I need to make a turn over here. How do I plan for that at the 20 to 30 second range? That is where the critical issue comes in, because it really doesn't do a particularly good job right now. So it's missing that sort of middle level of the hierarchy. And that's something that I contend that the kind of training that they're doing right now is probably not going to really solve that problem completely. And the main reason why, as Yann talked about, is the expense. And when he says it's expensive, he doesn't mean it costs money. What he means is it's compute expensive, right? If you wanted to say millisecond to millisecond, how my body is going to move through space to get me to Paris, it would take you probably, the rest of your life to calculate out that one trip. You would just be like, it'd be incredible. Also, it'd be really difficult because we don't really know. We just sort of unconsciously move. But if you could, sort of map out, let's say you were doing a humanoid robot, and you're mapping out with that humanoid robot, the millisecond to millisecond movements and everything. This is something you can do with industrial robots. This is something that Scott and I have talked about a lot, is with industrial robots, you pre-program them, but they do a thing that takes a few seconds. And so millisecond to millisecond planning is fine because it just repeats that action. Maybe it's a 10-second or a 30-second action that it just does a million times a year. It just does that thing over and over. That's fine. You can program that very, 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 get into the weeds and program it millisecond by millisecond and make sure it does exactly the right thing. That is not a viable solution when you're talking about a humanoid robot that might have to get into a car, might have to drive to the store, might have to go grocery shopping. I don't know. I'm just saying, making up stuff. But, it has to pick up the bags, which are squishy and everything. You don't know exactly where they are. There's no way that it can plan that stuff out. You can't pre-plan it and say, this is exactly how you're going to do. So you need by necessity a hierarchical level of planning, which means you need levels of abstraction that the vehicle or the humanoid robot, either way. And when I talk about full self-driving here, I'm talking also about humanoid robots as well. And not just Tesla, but also NVIDIA and their Gear Lab and their new Groot thing. And if you haven't seen that video, you should definitely check it out. It's really, really cool. But also Tesla's Optimus. Sanctuaries robot, Figures robot, Aptronics robot, Unitrees robot, and on and on and on. You know, they've got these things where they've got this sort of high level task planning that they need to do, which is basically, can you go grab me a beer out of the fridge? And then it's got to stream that down to the very, you know, microsecond by microsecond activity of the joints, which is analogous to the way that we work. So that, as Yann says, that's an unsolved problem. And this is where, you know, Tesla keeps coming up against this over and over and over again. And I keep complaining about it. And I'm not complaining about it in the way of like, you guys, you know, you're so stupid, you should be able to figure this out. It's like, how do you figure this out? Well, this is where JEPA comes in, where visual JEPA comes in. And that's really intriguing to me.
Can you use an LLM, state-of-the-art LLM, to get you from New York to Paris by doing exactly the kind of detailed set of questions that you just did, which is, can you give me a list of 10 steps I need to do to get from New York to Paris? And then for each of those steps, can you give me a list of 10 steps how I make that step happen? And for each of those steps, can you give me a list of 10 steps to make each one of those until you're moving your individual muscles?
There's a lot of questions that are sort of implied by this, right? So the first thing is, LLMs will be able to answer some of those questions down to some level of abstraction, except they're not going to be able to really kind of produce millisecond by millisecond muscle control of how you stand up from your chair, right? So, but down to some level of abstraction where you can describe things by words, they might be able to give you a plan, but only under the condition that they've been trained to produce those kind of plans, right? They're not going to be able to plan for situations where that they never encountered before. They basically are going to have to regurgitate the template that they've been trained on.
But where, like, just for the example of New York to Paris, is it going to start getting into trouble? Like, at which layer of abstraction do you think?
LLM would be able to solve that problem if you fine tune it for it. You know, just and so I can't say that an LLM cannot do this. It can do this if you train it for it. There's no question. Down to a certain level where things can be formulated in terms of words. But like, if you want to go down to like how you climb down the stairs or just stand up from your chair in terms of words, like you can't do it. You need, that's one of the reasons you need experience of the physical world, which is much higher bandwidth than what you can express in words, in human language.
So everything we've been talking about on the joint embedding space, is it possible that that's what we need for like the interaction with physical reality for on the robotics front, and then just the LLMs are the thing that sits on top of it for the bigger reasoning about like the fact that I need to book a plane ticket and I need to know how to go to the websites and so on.
Sure. And a lot of plans that people know about that are relatively high level are actually learned, but most plans that people use are plans that they've been trained on, like they've seen other people use those plans or they've been told how to do things, right? Like you can't invent how you like take a person who's never heard of airplanes and tell them like, how do you go from New York to Paris? And they're probably not going to be able to kind of deconstruct the whole plan unless they've seen examples of that before. So certainly LLMs are going to be able to do this, but then how you link this from the low level of actions, that needs to be done with things like VJEPA that basically lift the abstraction level of the representation without attempting to reconstruct every detail of the situation. That's why we need VJEPAs for.
Okay, there's so much more that I could watch in this video, and I actually probably will come back to this video again and talk more about other things, because he talks about high bandwidth learning and things like that, about, embodied AI, which I am a big fan of. I think that in order to get to artificial general intelligence, or more specifically, artificially intelligent agents, we need embodiment. And actually, we just saw with Groot that we're getting that same sort of thing, which is that they're using a virtualized space, but it's embodied robots in a virtualized space that are learning to be agents in that space, and then there's zero-shot transfer of that virtualized space to reality in many, many cases. So I'm a big fan. I really, really feel like embodied AI is the way to get to actually, artificially intelligent agents here. And Yann agrees with this, and he goes into a lot of detail about that. But outside the bounds of this particular video. Like you can tell I'm very excited about all this stuff. But in this case, what he's referring back to is JEPA, or visual JEPA, which is that joint embedded predictive architecture that he's talking about and how it's necessary to get to hierarchical planning. Really interesting discussion. I actually cut out a few pieces of this LLM discussion just for time's sake. But again, go back and watch it. It ends at about 50 minutes or so. So, that 45 to 50 minute range. But anyway, the idea here is that large language models are able to do some of this, but Yann thinks that the transformer architecture, the neural network architecture of transformers and diffusion models and stuff is missing a key ingredient. I actually agree. I feel like these architectures are not perfect. And his rationale for this is, number one, that these things are disembodied, because when you deal with large language models, you're dealing with something that's already an abstraction from reality, because you're dealing with language, and language is not reality. It's an abstraction. It's a description of reality. But then the second part is you need tons and tons and tons of data to work with a transformer architecture in order to train something. And Tesla is seeing this right now. Of course, they need tons of data in order to teach the bots, whether it's Optimus or your car or something. They need a ton of data with this. And what Yann is suggesting here is that JEPAs are able to circumvent this by not being generative, but being able to be hierarchical. So let's take a look at JEPAs. So I'm over on Meta's website, ai.meta.com. Of course, I will leave a link to this in the description as well. We've got V-JEPA, the next step towards Yann Lecun's vision of advanced machine intelligence, or AMI, which is a great term. In French, it means friend. And he likes that better than AGI because, it's a advanced machine intelligence, and it also means friend. So he's going with friendly. So I actually appreciate that very much. So you can see it's about a month ago, February 15th. Unfortunately, everybody always puts music in these demos. So I'm going to cut the music out, but leave the, I think that this is actually a very good description, and it goes through very quickly, just a little over a minute, but it's also got text on the bottom, so you'll be able to read this, and I'll kind of go through as we're talking about it. So new architecture for self-supervised learning, or AI research by Meta. What we want to do, we need joint embedding predictive architecture is to create highly intelligent machines that can learn as efficiently as humans. So it's pre-trained on video data, of course, allowing it to efficiently learn concepts about the physical world, similar to how a baby learns by observing its parents. So this is very similar to what we saw with OpenAI and Sora and several other attempts at this kind of thing right now, which is learning from video data to interpret a three-dimensional world, to create a world model from two-dimensional data into actually kind of one-dimensional data in a way, because it doesn't have binocular vision. So I guess it's 2D, but anyway, it doesn't have full access to 3D. I think that video data is substandard ultimately. It would be better if we had access to 3D data, but of course at internet scales we really don't have that, so we're kind of stuck with what we have. So anyway, we're going 2D to 3D, but it seems to be working. Anyway, so it's able to learn new concepts, and you're going to watch this guy tear a piece of paper, and JEPA is able to go like, you're tearing a piece of paper, right? So here we go. It says, tearing something into two pieces. So that's what it thinks is happening without fine tuning. And JEPA is non-generative. This is really, really important. So we've got a masked input video here. And what it's doing is it's taking, and it's a chunk, it's a big chunk of masking here, right? You can see that most of this video is gone. And so what it's having to do is go in there and look at what remains of this video. And Yann describes this as like a tube. So imagine that every frame of a video, like 30 seconds long or whatever like that, it forms like a big block, right? And so each frame is like a slice of it or something like that. And what you do is you drill out a hole in that whole block. You're just like, whoop, you just make a hole in the whole thing, and it's a big hole, right? You can see this is a very large hole. And what it does is it masks this out, and then it trains JEPA, like, hey man, tell us what's going on in the rest of this video right now. Predict to me what is going to happen. So Yann is very specific. He's like, you can't take out little tiny chunks of it because that doesn't make sense, because it's too easy. And autoregressive training has been doing this for years. Andrej Karpathy talked about this ages ago with like stop signs and stuff, where you can pull out pieces of a stop sign, and then you can have it train on those images and say like, hey, what's actually going on in this, and can you please fill in that space? That's generative AI. That's going like, can you please put the pixels back in to regenerate the original image? So again, imagine you have an octagonal stop sign, and you cut out a piece of it. And what you're doing is you're asking the generative AI to fill that in, and that generates information. Here, what you would be doing is you would be asking the AI, if it was generative AI, you'd say like, please fill in the space. So in this case, I think the guy's, tearing paper here, it looks like. And so what it would be doing is trying to fill in all the details of that. But as Yann says, if you think about like the way that a human being interacts with the world, we see the world in very, very we don't really focus on most of this stuff. So you see a tree. What do you see? You see tree, and you're like, okay, and maybe you're like pine tree versus maple tree versus Bradford pear tree or something like that. What you don't do is I see, 35,000 leaves that are all moving gently in the breeze. Now you might say I see a tree in the breeze because you see motion of the leaves and everything, and maybe the branches if it's a big wind, but you don't go in and individually kind of regenerate in your mind all of those details. It would be insanely computationally expensive for our brains, and we don't do that. So here we've got the same thing. What they're doing explicitly here with JEPA is they are not asking it to fill in the blank. They're asking it to say, what is going on here? So in a way, it's kind of a classifier. It's like, what's actually happening in this space right now that you cannot see? That's the important part of this. So let's go back to the beginning of this, right? So you can see that this is a guy with a piece of paper, masked video input. We've masked out most of this thing. And then what we're asking it for, predicting missing parts of masked parts of a video in an abstract representation space. So that's important because we're talking about latent space for all of this stuff. So latent space, of course, is like a compressed version of reality. You can think about it as the way that we interact with reality. Again, I'm staring at two computer monitors, a camera, another camera, some lights, mouse, microphone, all of that kind of stuff. I compress that down into some sort of representation space that I might encapsulate as my office, right? So that's the kind of thing that I think about. I can squish this all down into an idea, and I can have kind of a three-dimensional, high-level I don't know. I guess, if I was out and about, somebody might say, hey, where's the this glass in your office? And I would be able to probably go back and say, like, it's on the notepad that's to the right of my mouse pad, which is in front of my camera and all that kind of stuff. So I would be able to reconstruct that, but I don't know every single detail. I couldn't tell you, pixel accurately where the logo is on this and all that kind of stuff. So I'm not regenerating it. I've compressed it into some sort of abstract representation. And that's what they're asking JEPA to do here. They're saying create a latent space that will allow you to understand these videos, and many, many, many of them, right? Not just a few, but create this latent space where you're able to then fill in the blanks and predict what's going to happen, which is where the P comes in, predictive architecture. It's predicting, not generating. It's a very, very critical difference. And we'll see that when we look at the text here, right? In an abstract representation space at latent space, unlike generative approaches that try and fill in every missing pixel, V-JEPA has the flexibility to discard irrelevant information, which leads to more efficient training. And that is really important, right? So we've got something that it just doesn't matter. Visualization of sample predictions, right? This is more along the lines of generative, I guess. I'm not exactly sure. But anyway, it's more about predicting what's going to happen next rather than, or predicting what is going on currently, I guess. It's not just what's happening next, but you take in the video and it's like, okay, what's going on in this video, which is why it's able to say like that person's tearing that piece of paper in two. And then they talk about, passing this on as open source information to other people. This is fantastic. Another important step in the journey towards AI that's able to understand the world. So it's all about understanding. It's not about generating. It's very, very different. So let's go through pieces of this paper, which unfortunately is not super, super detailed, but it's fine because there's a GitHub repository and all that kind of stuff if you're interested in looking into this more. Today, we're publicly releasing the Video Joint Embedding Predictive Architecture, or VJEPA model, a crucial step in advancing machine intelligence with a more grounded understanding of the world. So again, this is the same kind of thing that OpenAI is doing with Sora, just they're doing it generatively, whereas VJEPA is doing it understandingly. It's the same thing as if somebody said, can you describe your office, right? And I could describe it and all of these kind of things in a general sense versus can you please paint the office for me? Painting, that's going to require an immense amount of training to the level that I don't have to do it, a photographic representation of it. And probably you'd want to look at it anyway. You probably couldn't do it from memory. But that's going to require an immense amount more training than just what humans have naturally, which is the ability to go back and describe the office and to say, I've got 2 monitors and a camera and lights and blah, 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 right? That's relatively easy for us humans that most of us can do, at least who have, kind of standard intelligence, we can do that. Whereas for somebody to repaint that or create a drawing of it or something like that would take years of specific training in order to get to that level. And we would still probably want to look at a picture of it or look at the actual scene rather than try to do it from memory. That would be an immensely difficult task. So if you think about machine learning, it's trying to do that, to regenerate this stuff. It's like, wow, that's a really, really hard task to do that. Much, much easier to try to train it up to think about things in a more holistic manner, in a way that it understands stuff, but it doesn't have to regenerate that. Second takeaway, this early example of a physical world model, again, it's modeling the world here, excels at detecting and understanding highly detailed interactions between objects. So again, it's not just static, it's like it's describing tearing a piece of paper into 2 pieces. That's really interesting because it's a dynamic description of the world, not a static description. And then they say they're releasing it, Creative Commons non-commercial license for researchers to further explore. So really, really cool that they're doing this. I gotta say, I mean, I'm a big fan of Meta. I was not a big fan of Meta a couple of years ago, but with Llama and under Yann Lecun's directorship, I guess, and his influence, they've become really, really good at releasing a lot of open source material. And it's a big advantage to the world. Lex and Yann talk about this to a large extent because, Lex goes like, what is the business case for this? And Yann dances around it a little bit, but anyway, I find it very interesting, but definitely watch the interview. You'll get more information about that. And if you want to pause this video, you can read the other text, but again, I'm going to kind of skip down in the interest of time. Yann says here, our goal is to build advanced machine intelligence that can learn more like humans do, forming internal models of the world around them to learn, adapt, and forge plans, very important here, efficiently in the service of completing complex tasks. So again, go to New York or Atlanta to Paris or whatever. Again, that's a complex task that needs multiple levels of hierarchy in order to solve the problem. And again, to bring this back to full self-driving and or humanoid robots like Optimus, you have a complex task which might be like drive to the airport or something that has multiple levels of hierarchical planning that need to happen and alterations minute to minute as things change, as traffic conditions change, as the weather changes, as there's a detour, whatever happens, those kinds of things necessitate the ability to dynamically change according to the circumstances. And that's something that, at least in my observation, Tesla's full self-driving is really poor at doing right now. All right, so now let's get into the weeds a little bit and try to figure out how this all works. VJEPA in focus. VJEPA is a non-generative model, again, that learns by predicting missing or masked parts of a video in an abstract representation space. So that's actually very useful that we saw that video demonstration of this. This is similar to how our image joint embedding predictive architecture, or VJEPA, compares abstract representations of images rather than comparing the pixels themselves. So again, that's pulling it into an abstract latent space. Unlike generative approaches that try to fill in every missing pixel, VJEPA has the flexibility to discard unpredictable information, which leads to improved training and sample efficiency by a factor of between 1.5 and 6x. So again, in a video, it doesn't have to generate thousands of leaves moving in the wind accurately. You can throw that stuff out because it's not generative, it's only predictive. And a sample efficiency of 1.5x is not fantastic, but 6x is pretty darn good. You can go from 6 billion samples down to 1 billion samples. That's a pretty massive achievement in terms of the efficiency of training and also of data collection as well. Because it takes a self-supervised learning approach, VJEPA is pre-trained entirely with unlabeled data, so that's very important because that doesn't involve humans doing this stuff. Labels are only used to adapt the model to a particular task after pre-training. So that's kind of like the reinforcement learning, icing on the top of the cake kind of thing. This type of architecture proves more efficient than previous models, both in terms of the number of labeled examples needed and the total amount of effort put into learning even the unlabeled data. With VJEPA, we've seen efficiency boosts on both of these fronts. So again, you don't need labeled examples to do the foundation model stuff. You just need it for like kind of the icing on the top, the reinforcement, the fine tuning kind of training, stuff like that. So you don't need nearly as many of those. And then the amount of compute that's necessary to learn this stuff. And then specifically how they do this, with VJEPA, we mask out a large portion of a video. So again, large portion. So we're looking at here, you can see this in the example here. They've masked out most of this video, which I guess is a dog with a person walking. And they're asking what's going on here. So the model is only shown a little bit of the context. We then ask the predictor to fill in the blanks of what's missing, not in terms of actual pixels, but rather as a more abstract description in this representation space. So this is where we get to joint embedding, right? We've got two embedders, two encoders. We've got a context encoder, and then we've also got a target encoder. And then we've got a predictor, and this is ultimately what you're interested in here. And what you do is you train the predictor, you get a loss. It's like, well, that didn't work right. It thought it was a cow or a mouse or whatever. I don't know. It thinks it's the wrong thing. You pass that loss back through these three neural network models. They all kind of learn a little bit better, and they get better and better over time at doing this. And because you're doing this joint embedding thing, you can actually have it train itself for the most part. You don't need to actually label this as a dog. It just needs to learn to understand it in some sort of internalized language. And then the last step is you throw on top of this, can you please communicate with human beings in a way that we can understand? And that's the fine tuning that you can do, where it says like, oh, this is a dog with a person walking it or something. And again, note this blue highlighted thing, spatiotemporal regions. And what that means is you're blocking off a section of the video, but you're blocking it off over time. So again, think of it as a wooden block that's sliced, each frame is a little piece of that you're stacking together, and you're drilling a big hole through the middle of it. You're not randomly moving this around, you're leaving it as a giant hole throughout the whole thing as you train, and then you can move that masked part around as you want to continue the training. One thing that's really important about this is that the loss and the gradient descent requires that this stuff be differentiable. And that's an actual interesting aspect of VJEPA. And it's something that Yann and Lex go into in some detail in the discussion. So I highly recommend, again, if you care about the details of this, listening to their discussion, because they get into details about how this is differentiable and how you can then find a gradient and you can go and train this stuff so that it can actually get better and better over time. Then we get into the masking methodology. VJEPA wasn't trained to understand one specific type of action. Instead, it used self-supervised training on a range of videos and learned a number of things about how the world works. The team also carefully considered the masking strategy. If you don't block out large regions of the video, like I said, big chunks of it, and instead randomly sample patches here and there, it makes the task too easy. Interesting. And your model doesn't learn anything particularly complicated about the world. It's also important to note that in most videos, things evolve somewhat slowly over time, and that's worth thinking about, right? Stuff transitions from one thing to another over time. Now, an interesting part is, what if you had a video that had a bunch of quick cuts? It was like 1 second from this angle, 1 second over here, 1 second over here. VJEPA might not be good for this, but that's not something that you're going to see with a humanoid robot or with full self-driving. So for these cases, everything evolves slowly over time at 30 frames a second or whatever. It's very, very small changes from frame to frame. So that's a big advantage that VJEPA has, especially with interactive live video. Continuing on, if you mask a portion of the video but only for a specific instant in time and the model can see what came immediately before and or immediately after, it also makes things too easy and the model almost certainly won't learn anything interesting. As such, the team used an approach where it masked out portions of the video in both space and time, which forces the model to learn and develop an understanding of the scene. Then we get to efficient predictions. Making these predictions in the abstract representation space, again the latent space, is important because it allows the model to focus on the higher level conceptual information, remember hierarchical planning, of what the video contains without worrying about the kinds of details that are most often unimportant for downstream tasks. After all, if a video shows a tree, you're likely not concerned about the minute movements of each individual leaf. One of the reasons we're excited about this direction is that VJEPA is the first model for video that's good at, quote, frozen evaluations, which means we do all of our self-supervised pre-training on the encoder and the predictor, and then we don't touch those parts of the model anymore. In other words, they're trained and then they're not retrained after that. When we want to adapt them to learn a new skill, we just train a small, lightweight, specialized layer or a small network on top of that, which is very efficient and quick. And then skipping ahead a little bit, you can see down here from this image, what they've done is they've pre-trained this stuff without needing labels, right? So it can do it all itself, very, very efficient. You freeze the encoder, you freeze the predictor, and then you add on top of it, an image classification decoder, which is really relatively lightweight, an action classification decoder, that's relatively lightweight, a spatiotemporal action detection system that it's a little bit heavier, but it's not that heavy either. So all of these neural networks can be trained very, very rapidly with relatively few labeled data sets. In other words, some demonstrations or things like that a human can do, or some video examples or things like that. So it's a little unclear how many you've got here. In fact, I don't know. I don't believe, that the table actually shows that information. But so it says few shots, so it could be 5, it could be 50, I don't know. But it's pretty easy to come up with, say, 50 examples of something like that, or record it yourself if you need to and label those things. So that part can be done really quickly with a relatively small amount of data and a really, really small amount of training compute. Similar to the way that you can take diffusion models and you can slap a LoRa on top of that, which is another matrix with a relatively lightweight amount of data there that just adjusts the initial weights to create something like anime or something like fantasy or whatever it is that you want. You can create a LoRa for those kinds of things. This is a similar type of idea. You're freezing the original gigantic neural networks that take a ton of time and data and effort to train, and you're just putting a layer on top of that that is an interaction with the user to provide useful data for a specific use case. And here the caption says, a self-supervised approach for learning representations from video, V-JEPA can be applied to various downstream image and video tasks without adaptation of the model parameters. That's the really important part. You don't have to go back and retrain this giant model. V-JEPA outperforms previous video representation learning approaches in frozen evaluation on image classification, action classification, and spatiotemporal action detection tasks. So that's what Yann and Meta have come up with. They've come up with this predictive architecture that's very, very different from a generative architecture. And what he's claiming here is that this is going to be better at hierarchical planning than the current state of the art with transformers or with diffusion models or whatever that is. So this is a really interesting alternate way of thinking about things. It's essentially pulling out all of reality into an abstract latent space and saying, can you please make predictions or make plans based on this abstract space, ignoring the details, just give me the, the most salient, important parts of what you're doing right now. And so let's flip this back to Tesla and full self-driving and Optimus, the humanoid robot, or any other humanoid robot that's doing this kind of planning. This can be incredibly important to that. Again, we're looking at this 20 to 30 second range, which is a really nice chunk of video. That's a good amount of time. It can fit in memory. All of that kind of stuff can happen. You can pull it into an abstract space and say, can you please prepare? Can you plan for things, not millisecond by millisecond to make sure you don't hit another car, but on the order of where do I need to be? Where should I localize myself? What kind of actions should I take now to set myself up for success 20 or 30 seconds from now? And if V-JEPA works the way that Yann Lecun is talking about here, this is the kind of thing that it would excel at, and it would allow Tesla to have that intermediary step between Google Maps and millisecond by millisecond planning to not hit other cars and things like that. It would give it that middle section, the ability to hierarchically plan actions to have success in the future in terms of, a half a minute in the future, that kind of range. And the same again would go for a humanoid robot, like Optimus or whatever. You tell it what you want it to do in a very, very abstract manner, and it would be able to then hierarchically plan out the tasks in an environment that's kind of a latent space, efficient way of doing that. And then it would be able to create a hierarchical plan of how to go about those tasks. So this would be a huge advance in the ability of humanoid robots and also full self-driving to be able to plan in that 30-second range. And then finally, the other important part about this is it only requires data. It doesn't require very much human intervention because it can learn this stuff on its own. And that's critically important, right? So if you think about what Tesla can do, they have billions of miles of data that they can train on. They can take this data, this 360-degree, camera view that they've got, and they can punch huge holes in that data, and they can run it forward 30 seconds and say, what's going on? What do I need to be doing in the next 30 seconds? What would this human driver have done? What did this human driver do to get into the right lane or something like that? And especially for corner cases that are kind of complex, how did the human do this? Predict, tell me what the human is doing, what these kind of things are doing. If you can do that in training, the car can then predict what it's supposed to be doing in the next 20 or 30 seconds, and it can start to learn how to behave more like a human being by utilizing JEPA as opposed to trying to come up with a generative model where it actually generates the scene going forward. We've seen evidence from Tesla at last year's CVPR and from Elon Musk's tweets about this, that it can do generative stuff. It can actually do something like Sora, where it can actually generate what the future looks like from the current moment, but that's not really necessary for full self-driving. It's more important that it's able able to predict the future and what it needs to do to take action in that space to be able to figure that out. And that would be that spatiotemporal action detection head that you would put onto this thing. It would detect what it's supposed to be able to do in time and take action to make that happen. So this is very exciting in my mind. Now, of course, Tesla engineers are always up on this stuff, so the odds are in the last month that there have been a lot of discussions about this already. I don't know if they'll roll it into what they've got because I don't know how it would fit with their current stack, but it certainly seems like something that they should at least skunkworks out there, right? They should make an attempt at it and see if it improves that 20 to 30 second planning range, because still in my mind, that is the Achilles heel. That's the most critical thing about full self-driving that I feel still is not human yet, is that half a minute planning realm. All right, so that was a generally geeky episode, but I'm really, really excited about it. This is a really cool development. It's a new kind of architecture that I think has a lot of real potential. Definitely let me know in the comments what you think about it. And while you're down there, be sure to like and subscribe for more of this kind of content. In the meantime, I'll see you in the next one. Bye-bye.